theorem, which you can see there on page 43. So we're going to look at this today. We're going to prove it today. It's a nice, straightforward proof. It's a constructive proof. It's about how you put together solutions to systems of congruences, and how you kind of join a set of solutions to a number of congruences, how you kind of join them together in a way. And it's a very constructive proof. It's just kind of about laying down a formula and just explaining how the formula works. So as opposed to some kind of existence argument or anything like that. But we'll just start by just giving a little bit of motivation for, I mean, this isn't by any means the only reason why the Chinese remainder theorem is important, or the sole explanation of it, but it's a good piece of motivation for us, and it fits into the overall scheme that we're engaged with at the moment. Okay, so what we're working towards at the moment, okay, so I'm just going to sketch down here that we're working towards finding solutions of problem n, where f is some polynomial function. Remember, in this course, number theory course, we're talking about system of integers. So by polynomial, I mean a polynomial with integer coefficients. Okay, so the coefficients of all the powers of x are integers, of course. So we stressed that point already. Everything we're talking about is integers or congruence classes of integers and so on. Now, so this is quite a general type of problem. We've looked at examples already which show that there's no clear link as yet between the degree of the polynomial and the number of solutions. You can have polynomials which have no solutions at all, and you can have polynomials which have more solutions than the degree of the polynomial. So already things don't look as straightforward as they do with polynomial equations over the complex numbers, where the number of solutions is equal to the degree of the polynomial. Now we've looked at a special case of this already. So we've already analyzed the case of linear polynomials, case of order 1 polynomials, i.e. the problem of solving ax congruent to b modulo n. And this problem is solved completely by theorem 6.2, I think it was. Is it called 6.2? 6.3. Theorem 6.1 and 6.2 are leading up to it, but let's say theorem 6.3, 6.2, 6.1. Okay, so we understand completely linear congruences. We know when they have solutions, and when they do have solutions, how to identify them, and how to identify all the solutions. Okay, so we did some work in the tutorials this week with those. But as I say, we're approaching this general problem of solving these ones up here. Okay. The general problem above will be tackled using, well, we're going to break down the modulus n in a certain way. Now, what kind of way are we going to break it down? There's only one way we can break it down sensibly, given that we're in a number theory course, given the things we've looked at already. So what am I going to put on the right-hand side of this equation? There's going to be some way to systematically attack that general problem. There's really only one thing, one aspect of n that we could use. Something we attach the name fundamental to. Given the spirit of the course, how would you attack a problem which features the number n? There's a results that we've looked at lurking around. And the unique representation for n that there is a product of product using its canonical form. Okay, so n we know, so yeah, that's good. Every integer n can be written down like this, and this is kind of the in a number theory sense, this is, well, it's the canonical form of an integer. It's the way to represent an integer. It tells you a lot about it. You can see what prime factors it has, and you can see the multiplicity of each prime as a factor of it, okay? Using its canonical form. And so we will find solutions to the ground problem, f of x equal to 0, congruent to 0 modulo n. We'll find these solutions by solving, or by finding, systems of solutions, or sets of solutions, to f of x congruent to 0 modulo pi to the ai. So we're going to look at each prime power factor of n coming from its canonical form. And of course, there's a whole bunch of these. There's a bunch of these equations for each I equals 1 up to r. Okay, these are the r distinct prime factors that n has. So we're going to get our solutions for the general problem by finding sets of solutions of these. Okay, I'm not necessarily talking about simultaneous solutions. I'm talking about, so there's r different equations here when I runs from 1 to r. So we're going to find solutions to each of those. And so that'll give us a set of solutions for the system. And we're going to put these together in a way to find ourselves solutions to the original problem. Okay. And so the link between these two situations, so these two situations, by that I mean the solutions of this thing and the solutions of this set of congruences, is provided by the Chinese remainder theorem. CRT, the Chinese remainder theorem. So this is the thing that is going to connect solutions to this kind of thing to solutions of this ground problem. So it's just a bit of motivation, or a bit of, before we look at it, a bit of an idea to have in your back of your mind of the role it's going to play for us. And just before we leave this, just since I've kind of shown it to you now, in the next chapter, Polynomial Congruences 2, that chapter is going to be about looking at these types of problems and showing how to solve these. So also in the next chapter, we develop a method for lifting solutions. A process for taking solutions and lifting them up. So what do I mean by that? Lifting solutions from a congruence like this, a polynomial congruent to 0 modulo prime, taking solutions from that and lifting them to solutions modulo p squared, then lifting them to solutions modulo p cubed. So you get the idea. until finally you can build up or lift up solutions, starting by finding solutions to this kind of simple or bottom situation where a polynomial is congruent to 0 modulo prime, taking these solutions and lifting them up until you arrive at solutions to a polynomial congruent to 0 modulo whatever power of the prime you're interested in. Okay? So for solving the general kind of problem, we'll have to do this kind of lifting process for each of these I equals 1 to r, for each of these polynomial congruences there. So for finding the solutions to a general polynomial congruence, f of x congruent to 0 modulo n, we have to look at the canonical form of n, and then the problems that we start with are these problems here, f of x congruent to 0 modulo p for each of these primes. So we focus on them a prime at a time, say. We'll find solutions to these. In the next chapter, we'll describe this process for lifting those solutions up until finally we get to solutions to the final, to the polynomial congruent to 0 modulo the final power of the prime. And then once we have these solutions to all of these polynomial congruences, we'll be able to kind of glue all those together using the Chinese remainder theorem until we finally arrive at solutions to the initial problem. Okay. So that's not talking about any of the details of it. That's just giving you just the broad brushstrokes of kind of the kind of major moves that we're going to go through in order to solve this kind of problem. Okay. So coming back to now, so let's make things very concrete now and start talking much more precisely. So we're going to look at the Chinese remainder theorem now, which is in section 6.3. Okay, and this is the name Chinese remainder theorem because the kind of problems that it solves have been found in some of the very early Chinese literature coming from around the 1st century AD. These kind of problems have been recorded in mathematics, or in manuscripts that have come from that time. For instance, problems like this: find a number which leaves remainders 2, 3, and 2 when divided by 3, 5, and 7 respectively. So you're asking yourself, is there a number which when you divide it by 3 leaves a remainder 2, when you divide it by 5 leaves a remainder 3, and when you divide it by 7 leaves a remainder 2? Maybe there is such a number, maybe there isn't. Maybe there's an infinite number of them. Maybe there's not, maybe there's just one, maybe there's 5 of them or something. Yeah. So being able to solve those types of problems. Now, of course, when we talk about dividing integers by other integers and leaving remainders, you know, your brains are hardwired now to make the connection. That's talk. That is talk about congruence classes. You're dividing integers by other integers, talking about the remainders they leave behind. You're talking about congruences. Okay, so this is the kind of modern presentation. Oh, what happened there? This is how we present the Chinese remainder theorem in our kind of modern talk about congruences. So this is the statement of the theorem. We're going to assume we have a bunch of moduli, m1 up to mk, and we're going to assume something fairly strong about them, that they're pairwise co-prime. That's a phrase that features in one of your coursework problems. Well, the coursework problem doesn't involve the Chinese remainder theorem, but it's this idea of being a set of numbers being pairwise co-prime, meaning if we take any two of them, we take any two different numbers, they're co-prime to each other. They're the greatest common divisor of 1. Now, immediately when I say that, a bunch of numbers being co-prime to one another, we see that in the canonical form. These numbers, that are multiplied together in the canonical form, different prime powers, the different powers of primes, these numbers are all co-prime to one another, okay? You take any two of these brackets and ask for their greatest common divisor. Of course, the greatest common divisor is 1, because the two different brackets will each be powers of different primes, okay? So these brackets are very definitely pairwise co-prime. Okay, but we're not insisting that these moduli mi be of this form, be powers of primes, but just that this is a natural example of where you encounter a bunch of numbers being pairwise co-primes in the canonical form. Okay, so we're going to look at a simple set of congruences. Basically, we're looking at a different for each of these moduli mi, we're identifying one of the congruence classes. So we want to talk about the congruence class of B1 mod M1, B2 mod M2, etc., up to BK mod MK. So we're singling out one congruence class for each of the moduli. So the way we'll encounter this when we're tackling our general polynomials is this will be a set of solutions, to each of these polynomial congruences. So this number here, when we apply the CRT to our problem of solving polynomial congruences, these prime powers will be the mi, and these bi's will be a solution to each of these, okay? So this will be, we'll have a solution x congruent to bi modulo this of this polynomial, okay? So that's the way we're going to encounter it. Okay, but what does the theorem say? What it says is that if you think of the product of all these moduli, which in our case, when you multiply together all these prime powers, that gives you your original modulus n. If we think of the modulus formed by multiplying all these together, what the theorem says is that there's a unique congruence class, modulo this big integer here. There's a unique congruence class which is congruent to each of these, okay, which kind of projects down to each of those. Okay. Or in other words, just to kind of phrase it slightly differently, because this might be, yeah, I'll give you an alternative phrasing of that just to make it very clear or explicit what we mean. So the same setup, it's just kind of a reformulation of it, i.e. there exists a unique congruence class. So you should take this down as an alternative formulation of the outcome here. A unique congruence class, so say it'll be the congruence class of B modulo capital M, and capital M is the product of all these little m's, goes up to k, such that this integer b, or this congruence class here, is congruent to the little bi modulo the little mi. Okay. So we've got these different little b's, b1, b2, up to bk. And the theorem is saying that kind of upstairs, there's a unique congruence class modulo capital M, which is the product of all these. The unique congruence class up there that projects down onto all of these. I'm thinking, you know, I like to think of this have a kind of geometric metaphor. I like to think of this as projecting down. There's this unique integer upstairs, could be very small, smallish, which projects down onto each of the BI. Okay. So the theorem is saying two things. It's saying there is something upstairs which projects down onto each of those. And secondly, it's a unique, there's only one congruence class of such things, modulo capital M, okay? So there is an infinite number of choices of integer b, which will do this job. But they all belong to the same congruence class, modulo M. So that's nice, okay? So think of this theorem as saying, you know, it's just pointing out a really nice link between congruence classes modulo a bunch of these little m's and the way they kind of all lift uniquely to a single congruence class modulo the capital M, which is the product of all of these. But now an important condition needed for it is that these individual little moduli you're starting off with, they are pairwise coprime. Okay? If you don't have the pairwise coprime condition, then the theorem will break down. And there will either, I think I'm right in saying, you will, if you don't have this coprime condition, you'll be able to write down examples where there won't be any integers capital B that project down, or indeed, you'll be able, I think you might be able to write down examples where there are multiple different capital B's from representing different congruence classes that will all project down onto these individual congruence classes down here. Okay. Okay. Now, maybe I was thinking maybe we should look at an example first. Well, just an example of the kind of problem that this is going to solve is, well, this is this first problem we wrote down that you can find in this early Chinese text. We've got x congruent to 2 modulo 3, x congruent to 3 modulo 5, x congruent to 2 modulo 7. The moduli 3, 5, and 7 are very definitely pairwise coprime. So the Chinese remainder theorem says that there's a unique congruence class modulo the product of these, which is whatever it is, 3 times 35, 105. There's a unique congruence class 105, which will be congruent to 2 mod 3, 3 mod 5, and 2 mod 7. Okay. Maybe you could write, you know, if you just kind of stare at that for a minute or two, the numbers are low enough, you might kind of pick out the number that it is. But, you know, if you start talking about these numbers here, suddenly things are getting larger. So we need a general proof for this. And the proof is quite nice. The proof is very constructive as opposed to an existence type of proof. So up here, so the proof starts in the previous page, but up here at the top, you can see a big long formula for the x. So this is the formula which gives the thing we're looking for in the theorem. Okay, and there's a bunch of ingredients that goes into the formula. So the proof of the theorem is about defining each of these ingredients that are in this formula for x here, and secondly, proving that this does the job claimed by the theorem. That this number x, which we give a formula for there, does project down onto each of these. And lastly, as so often in these things, we prove the uniqueness bit at the end, which we probably do by a proof by contradiction, I think. So we suppose we have a different solution and then show that we get a contradiction if we suppose there is a different solution. Okay. Now you see in this formula there are numbers b1 up to bk. Okay, they're the numbers that are in the original statement of the problem. Then there's all these capital M's, capital M1, capital M2, and some related numbers, capital M1 prime, capital M2 prime. So we need to understand what these are. We define these numbers, and then you start to see the reason for that formula being as it is. Okay. So first of all, we denote by, and this is the same notation I've used here on the whiteboard, we denote by capital M the number which is the product of all the little m's. Okay. let me just, at the same, it's probably good. Well, we've two choices. Either we'll work through the proof and then do the example, or we can be running the example as we're looking at the proof. I think it might be good to run the example as we're looking at the proof. Because this is one of those occasions where looking at an example kind of does show you the full story. Okay. Normally looking at specific examples maybe doesn't get across the full reason for things, but I think this is a case where it does. So this is this first example. So these are our three congruences. So this is our M1, M2, M3. These are our B1, B2, B3. That makes them look like powers or something. I won't do that. Those are the B1, B2, B3, and these are the M1, M2, M3. So first of all, we talk about this number, capital M. So capital M is the product of my three moduli, which here is 105, isn't it? 15 by 7, 105. Okay. Then we define three other numbers. Now, M1 is the product of all the moduli except M1. So it's the product of 5 by 7, 35. M2 is the product of all the moduli except M2. That's 21. And M3 is the product of all of them except M3. So that's 15. Okay. So you can see how that's represented there in the proof. The capital Mi is equal to the capital M divided by the little mi. So it's the product of all of them except the little mi, because you're dividing by the little mi, so that knocks it out of the overall product capital M. Now, there's a little note here, which is something which is significant later on. As a consequence of this, the capital Mi is congruent to 0 modulo little mj for any I not equal to j. That's a bit of a mouthful. That's just noticing or pointing out things like this, that capital M1 is congruent to 0 modulo 5 and congruent to 0 modulo 7. Okay, because it's got a factor of 5 and a 7 in it. Similarly, capital M2 is congruent to 0 modulo M1, which is 3, and it's also congruent to 0 modulo 7, which is M3, because M2 has got factors of 3 and 7. So the consequence of how we define these numbers, capital Mi, that this is true. Each of the capital Mi is congruent to 0 modulo all of the other little moduli. N's. Now, also notice that capital Mi is co-prime to little mi, where the index is the same. So where the index is different, it's congruent to 0, but where the index is the same, it's co-prime. So this is another noticing. Notice capital M1, little m1, i.e. here, that's the GCD of capital M1 is 35, little m1 is 3. That's co-prime. Okay. Also, the GCD of capital M2, little m2, so that's the GCD of 21 with 5. That is also 1. That's also co-prime. Okay. That's a consequence of the fact that the little m's are all pairwise co-prime. Okay. These little m's are all pairwise co-prime to each other. So when you multiply a bunch of them together, but leave out one of them, so multiply them all together except for one of them, that product is going to be co-prime to the one you've left out, okay? Because they're all pairwise co-prime. All the things you've multiplied together, each of them individually is co-prime to the one you left out. So therefore, when you look at them in a product, as a product there, it's co-prime to the one you left out. Now, the important thing here about being co-prime is when you've got one number that's co-prime to another one, it means that the first number is invertible modulo the second number. Okay? And that's these numbers, capital Mi prime. Those are the inverses modulo little mi. Okay? So because of this co-prime condition, we know that there exist out there somewhere these integers capital Mi prime, which are the multiplicative inverses of capital Mi modulo little mi. So let's find each of these for our example here. So my M1 is 35. So my M1 prime is going to be the inverse of 35 modulo little m1, which is modulo 3. Now, to figure out what that is, I should just immediately reduce this modulo 3. So what I'm talking about really is the inverse of 2 modulo 3. What's the inverse of 2 modulo 3? 2. 2 by 2 is 4, which is congruent to 1 modulo 3. So M1 prime is 2. Nice and simple. M2 prime is supposed to be the inverse of M2, which is 21, modulo 5. What's the answer to that? When you go into the number theory exam, you want to be like firing on all cylinders. Someone throws it up in the air, it's going, shoot it down. What's the inverse of 21 modulo 5? 1. 21 is 1 modulo 5. The inverse of 1 is 1. Good. So M2 prime is 1, even simpler. M3 prime is the inverse of 15 modulo 7. You shoot it down. What is it? 1. Yeah. So 15 is congruent to 1 modulo 7, so it's its own inverse. So it is 1. That's nice and simple. My M1 prime is 2, my M2 prime is 1, my M3 prime is 1. But remember, so that's what they are in this example, but remember what they are generally. Capital Mi prime is the multiplicative inverse of capital Mi modulo the little m. Okay. Remember that the little mi is the modulus that was left out in forming this capital M product. Okay? Because the capital Mi was the product of all of the moduli, but we cancelled out the little mi. Okay, so that's a whole bunch of new stuff to stick in your head, but that's all the ingredients now for our grand solution. Okay. And the grand solution, as you can see, are, first of all, any questions about any? You're probably unsure a little bit about how it's all going to fit together and give us a solution, but anybody unclear on anything? Okay. So the final solution is this number x, which is given here. So it's really nice and simple in some ways. It's just this summation. You add up all these products, bi, capital Mi prime. Obviously, I going from 1 to k, whatever the k is in this problem. Now, this is where, yeah, so let's write this out, what this is for our example. So what was our B1? Our B1 was 2. Our capital M1 was 35. And the multiplicative inverse of 35 was 2. And will everybody see if I wrote this down? Yeah. The B2 was 3. Capital M2 was 21. And the inverse was 1. Might as well write it down. And then the last term is B3, which is 2, times M3, which is 15. And it had the inverse 1 as well. Now, slow down and stop if you're already working out what that is and adding it all together. Don't. Leave it separated. Leave it spread out like that, okay? Because that's how we have to look at it and consider it now. The claim is that this number x we've written down is the solution, or is the solution that we're looking for. Now, what solution? Just look back at the statement of the theorem. We're looking for a number x, which is going to represent a congruence class modulo the product, and which is going to project down onto each of these. That x is congruent to b1 mod m1, congruent to b2 mod m2, and so on. Now, the claim is that this is the x that I've just written there on the whiteboard. So let's test this claim. What is the congruence class of this modulo the first m1, modulo 3? So you look at this number and you ask, what is the congruence class of this modulo 3? Well, the first thing you notice is this number 21 was designed so that it's got a 3 inside it. And this number 15 was designed so that it had a 3 inside it. So if we're talking modulo 3, these two are congruent to 0. There's a 3 inside it. So we're just left with this one. Now, this number 35 was designed to not have a 3 in it. So there's no 3s around here. But how are these numbers designed? The 35 and the 2, how are they designed? The 2, this 2 here, was designed to be the inverse, 35 inverse modulo 3. So when you're considering this modulo 3, these two cancel out because they're inverses of each other. So you're just left with the 2, which is the B1. So this number x is, in the way it's designed, in the way it's constructed, it is congruent to 2 modulo 3. Because these two are congruent to 0 because they were set up to have a 3 in them. And these two numbers were set up to be inverses of each other modulo 3. So they cancel out, they give 1, so you're just left with 2 modulo 3. Let's look at it again from the point of view of modulo 5. What is this number x modulo 5? Well, this is why we didn't multiply it and add it all together, because you lose the structure there. This 35 was designed to have a 5 inside it. And that 15 was designed to have a 5 inside it. So modulo 5, the first term is 0 and the third term is 0. So you just consider the middle term. But these two numbers were designed to be inverses of each other modulo 5. So they multiply together to give 1. So you're just left with 3. And the 3 is exactly the B2. 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 So this number x is congruent to 3 modulo M2. Same thing for 7. How does this number x perform modulo 7? Well, these two numbers here, the 21 and the 35, were constructed to have a 7 in them. I'm probably boring you now. I'm just saying the same thing, but it's instructive to observe that. These two numbers have 7 in them, so they're congruent to 0 modulo 7. 15 and 1 were designed. 15 and 1 were designed to be inverses of each other modulo 7. So they cancel to give 1, so you're just left with the 2, which is this 2 here, modulo 7. Okay. So we gathered these bunch of ingredients and stuck them all together like this. And you can see that the way we stuck them together guarantees that this number x is the solution that the theorem is asking, or that the theorem is claiming to find. Okay. So that explanation is just carried out in general terms here in the text of the proof. But it's exactly the same as the reasoning I just stepped through about that little example here. When you look at this number x, okay, the claim is that's the solution the thing is looking for. So you look at x modulo one of the mi. But we know that the capital mi's so we're looking at this x modulo little mi. The only term that's going to be left behind, the only term that's non-zero is the one featuring capital Mi and capital Mi prime. Okay? All of the other ones are congruent to 0 modulo little mi, just as it was in the example that we studied. But then, so x reduces to this modulo little mi, because all the others are 0, but then these two are inverses of each other modulo mi, so they cancel, or they multiply together to give 1. Modulo little mi, so you're just left with the bi. Okay? So when you look at this number here, with regard to any of these moduli, everything disappears except the one term, which has the relevant b in it, and the other two bits are inverses of each other, so they disappear. So this number x is constructed in such a way that when you look at it modulo mi, everything falls away except the bi. And that works for each I. That's the neat thing about it. So that's the proof that there are solutions that the theorem talks about. The only remaining thing is to address the uniqueness. Okay? That's that last paragraph there. What remains to be shown is that the solution in 6.27, the solution here, that is unique. So why is that? Why is that unique? So I think we do this by a little proof by contradiction, or I mean, it could be phrased like that. It isn't phrased as a proof by contradiction here, but what we do is we suppose that little y is any other solution to this problem. So suppose that little y is any other solution to this problem. So that means this x here, so this x here is this x that we've constructed here. This y, whatever it is, it has to be congruent to x modulo little mi, okay? Because they're each of them congruent to bi. Yeah? X is the solution we found. Y is some other solution we're supposing is out there somewhere. So the little y has to be congruent to bi modulo mi, but so is the x. So the x is congruent to the y modulo mi. But being congruent modulo mi means that little mi divides the difference. But crucially now, these little mi are all pairwise co-prime. So if you've got a bunch of numbers, so here's a single number, x minus y. And here we're pointing at a bunch of numbers that divide x minus y. But in particular, this bunch of numbers, the little mi's, they're all pairwise co-prime. So if we know that each of them individually divides x minus y, that means we know that the product of them all also divides x minus y. Okay? It's kind of because each of them is dividing x minus y for different reasons with regard to different prime numbers. So that you can glue them all together and the whole lot of them will divide x minus y all at once. Okay? So they're not treading on each other's toes. So we get that capital M divides x minus y. That's just another way of saying that x is congruent to y modulo capital M. So there are plenty of other integers out there which solve the problem apart from this integer x, but they are all congruent to this one modulo the capital M. Okay? And that's what the statement of the theorem said, that there was a unique congruence class has a unique solution modulo the product M1, M2 up to Mk. So what I'd like you to do is study that proof, really let it settle in, digest it. It all just hinges on the idea that we construct this number x, such that when you look, you kind of think of it as like you stick on a pair of glasses, which are modulo little mi glasses. And when you look at it, everything falls away except the bi, mi, mi prime. And the mi, mi prime are inverses, so they fall away, so you're just left with the bi. Okay. So it's a very nice example of what's known as a constructive proof. A proof that proves there is a solution by actually building it. So rather than just giving some vague existence argument that there has to be a solution without actually pointing to it or telling you what the solution is. It's a very nice constructive proof. And there's a whole bunch of examples here. So we simultaneously worked through this first example 6.41. There's another one there. There's a bunch of them in 6.2. And then another one of these problems taken from another one of these earliest texts, the Brahmagupta, an Indian text from around the 7th century AD. Talks about number of eggs in a basket and taking them out and what's left behind. So you should, when you think about the way that problem is solved, you should recognize that in our language, it's a problem about congruence classes. So you can formulate the problem about congruence classes and attack it using the Chinese remainder theorem. Okay, that brings us neatly to the end of that. Okay, so we'll begin the next chapter next week.